this is a talk about card shuffling, I am going to show you a card trick. Let's see. Are you able to ripple shuffle? No. No. Who can ripple shuffle? You can ripple shuffle? Okay. So here's a deck. It's an ordinary deck, but tell me your name.
Chan Wu.
Chan, okay. I'm going to ask Chan, though, to shuffle the deck for me, okay? And what I'd like you to do is just give it one ripple shuffle. You don't need to do anything fancy. Just shuffle the sides together. Oh, that's good. Okay. Whoa, a little flourish. All right, let's give Chan a hand. Okay, so would you agree that now that Chan has shuffled this deck, there's no possible way I could know the order of this deck? No possible way, yes? So then would you also believe I was born with an amazing ability to feel the color of the cards? Actually, it's not that refined an ability. I have no idea what color this card is. No idea, okay? But I can pull out cards in pairs that are opposite colors, okay? So this should be red and blue. Yes, okay, excellent. And this should be red and blue. Yes, yes, red and blue. This should be red and blue. Yes. Now the chances that I'm doing this by accident are, you can work it out. It's not quite a half, but it's close to a half if I'm just doing this random, pulling them randomly. Yes. Red and blue. And at some point you guys are going to clap because you'll be impressed that I can do this 5 times in a row. Or maybe even 6 times in a row. Or, thank you, maybe even 7 times in a row. In fact, are you now convinced I can probably keep going? Maybe even to the end of the deck? Yes? 8 in a row, okay. So that's a cool trick. Do you like the trick? Well, then clap. All right, great. So clearly something is going on. Even after one shuffle, somehow if you don't believe I have this amazing ability, then I must be somehow exploiting the fact that one shuffle is not enough to mix a deck of cards. Okay? Does anybody know how many shuffles it takes to mix a deck of cards? Anyone know? Yeah?
Is that 8 shuffles?
Yeah, that's a nice guess. Actually, how many shuffles do you think it takes? How many people here think a deck of cards takes, I don't know, around 8 shuffles? I'll give you the choices. How many people think it's about 8 versus 80 versus 800? Vote. How many people think it's about 8? About 80? About 800? Okay, yeah. So it's a reasonable question to ask. How many shuffles does it take to mix a deck of cards? We'll answer that. Let me ask you another question. Which of these numbers is largest? So just take a moment. Don't calculate. Just form a gut reaction. Okay, just pure. What does your gut say? Which is the largest number on this list? The number of stars in the universe, number of seconds since the Big Bang, and the number of ways to order a deck of 52 cards. Take a moment, form an opinion, and then I want everybody to vote. Raise your hand when you formed an opinion. Don't expect you to know the answer. Raise your hand. Commit. It's okay. No shame in just guessing. Yes? Everybody. Form an opinion. Raise your hand. Okay, good. Put your hands down. Now, let's vote. How many people think the number of stars in the universe is the largest? How many people think it's the number of seconds since the Big Bang? Interesting. How many people think it's the number of ways to order a deck of 52 cards? Interesting. Okay. Well, so I'll tell you what scientists believe. The number of stars in the universe is actually on the order of 10 to the 23. Okay, so that's 10, 1 followed by 23 zeros. This is the number of stars that's estimated to be in the universe. The number of seconds since the Big Bang is actually on the order of 10 to the 17. It's actually smaller than the number of stars in the universe. And then, of course, if you know a little bit of counting, you might be able to see that this is actually on the order of 10 to the 68. Okay? Hugely larger, yes? Way hugely larger. I mean, here's one way to think about it. If you think about the number of stars in the universe, if there were a universe for every star, and then you counted the number of stars, that's 10 to the 23 squared. That's still not as large as the number of ways to order a deck of 52 cards. Number of seconds since the Big Bang. Imagine somebody taking a deck and shuffling it once per second since the beginning of time. Look at how many configurations they would run through compared to the total number of ways to order a deck of cards, right? So another way to think about that is, in fact, if you just take all the people that have ever existed, imagine them shuffling the deck once per second since the beginning of time. It still wouldn't run through all the possibilities. So when you take a deck and you shuffle it, the amazing thing is the resulting configuration is probably the first time in the history of the world that configuration has ever been seen, right? So every time you shuffle a deck, you're making history. It's amazing, right? Amazing way to think about this. What's kind of surprising then is that you can say anything so precise as how many shuffles does it take to mix a deck of cards? I mean, there's 10 to the 68 possibilities. Now, of course, we know how to count these possibilities, right? One way to think about it is counting the number of ways the first card can appear, the second card can appear, the third card can appear, right? So if we just take a simple example of a 3-card deck, the first card could be A, B, or C, correct? And then once you pick the first card, the second card has one of 2 options, right? And then the last card is determined. So if you think about a 3-card deck, the number of configurations is going to be, going to be 3 times 2 times 1, right? And in general, for an n-card deck, there's going to be what's called n factorial ways to order the deck. And this comes from the fact that, now what is n factorial? N factorial is n times n minus 1 times n minus 2, basically all the way down to 1. Okay, so you're multiplying all the numbers from 1 to n. And this comes from the fact that the first card has n choices, the next card there are n minus 1 choices, the next card's n minus 2 choices, etc. Okay? You multiply all that out, you get 8 times 10 to the 67 for 52 cards. Okay, so we're going to refer to the 3-card deck a lot today because it'll just help us think about what's going on with 52 cards. So when you talk about shuffling, there are many different ways to shuffle. Okay, so the kind of shuffle that I just asked Jan to do is what's called a ripple shuffle, a standard ripple shuffle, sometimes called the Gilbert-Shannon-Reed shuffle, the GSR shuffle. There's another way that people shuffle the deck. It's often by just taking clumps from the top, like this, like that. How many people shuffle like that? That's an overhand shuffle, okay? And that's another way to shuffle a deck. Another way to shuffle a deck is just to throw them all up in the air and then gather them, right? Okay, that's called 52-card picking. Okay. Are there other ways to shuffle that people know about? Any other ones? Oh, okay. Yeah, so this is the top shuffle. Take one card from the middle and put it on top. Okay, so this is a very simple shuffle. Nobody shuffles like this. But mathematicians like thinking about simple shuffles to help us understand complicated shuffles. That's the top shuffle. Okay. Are there other shuffles? Oh yeah, here's another shuffle. What's called the perfect shuffle. So the perfect shuffle is you take a deck and you cut it exactly in half, and then you perfectly interleave the cards. Left, right, left, right, left, right. Okay? There's actually 2 kinds of perfect shuffles. There's the perfect shuffle where the top card stays on top, and the perfect shuffle where the top card goes to the second position. This one's called the out shuffle. This one's called the in shuffle. Okay? That's another kind of shuffle. In fact, some magicians use that kind of shuffle to manipulate the deck. All right, good. So lots of different kinds of shuffles. So mathematically speaking, what is a shuffle? There's a question. That's the first question you have to answer before you even answer the question, how many shuffles does it take to mix a deck of cards? Would you guys agree that all these versions of shuffles actually mix a deck? Right? The ripple shuffle, yeah, you mix a deck. Overhand shuffle, that's what you do, right? 52 card pickup, that mixes the deck. Top shuffle mixes a deck, probably very slowly. 52 card pickup, very quick, right? Mixes the deck. Perfect shuffle? Does that mix the deck? Interesting. But it depends on what you mean by a shuffle. We have to think about what we mean by a shuffle. Okay, so what is a shuffle? Somebody give me a definition of a shuffle. Just a thought.
I have a question. You're ordering.
Okay, you have a question?
Yeah. So how do you define a mixed deck?
We'll get there. We have not even defined mix yet. Yes, we first have to figure out what a shuffle is. And that's one of course, the things that's great about mathematics and modeling is that we have to make certain words precise. Okay, we're going to do that. What were you saying? What a shuffle is?
It's a permutation of the 52 cards.
Okay. What is a permutation?
It's a reordering.
Okay, so we'll think about a reordering, and we actually have to be a little careful here. So I like the fact that you said permutation. So a permutation is, if you like, a reordering of the deck. Okay? So it tells me that this card goes to this position, this card goes to this position, etc. Yes? It's a specification of where every card goes. Now, is a shuffle really a permutation? Like a single permutation? There's a little more going on, right? Because, for instance, when I do a shuffle, I can't tell you what the next, I mean, that's part of the point of shuffling, right? If I give you a thing, and if it were just a permutation, I should know after he did the shuffle exactly what configuration it's in, correct? Well, good. So that's the first insight here is, yes, it's related to permutations, but it's not just a permutation. So for instance, if I think about what a top shuffle is, with a 3-card deck, do you agree that the top shuffle has 3 possibilities that could result? Top card A goes to, it stays in the top position. Well, I guess this is backwards. Okay, yeah, so, sorry, there are 2 versions of top shuffles, and I just prepared my slide one way, right? One version of the top shuffle is you take a card in the middle and you put it on top. Another version is you take the card on top and put it randomly in the middle. Okay. And I've just drawn my slides one way. Yeah. So this is the version where you take the top and put it randomly in the middle. Okay, so tell me here what could result. Well, one thing that could result is the top stays on top. The other thing that could result is top goes to the second position or top goes to the third position, right? And each of these has a probability associated with it, right? So this might have probability 1/3 of doing this, 1/3 of doing this, 1/3 of doing this. That's what we mean by take the top card and put it in a random uniformly random position in the deck. Okay. So what you see is a shuffle is not just a permutation, but it's actually a collection of probabilities on permutations. So it's a probabilities on permutation. And if you ask me to specify this for every permutation, I mean, there are some permutations here that are not represented, right? This one, it does not exist, so this is probability 0. Right? So if you ask me to specify the distribution of every possible permutation, what I see is we'll get what's called a probability distribution. It's a probability distribution on permutations. So that's the key insight, is that that's what a shuffle is. A probability distribution on permutations. Okay? So every permutation has a probability. Specifies the probability of every permutation. For a 3-card deck, there's just 6 permutations. But for a 52-card deck, there are 10 to the 68 permutations. Okay, that's a lot to specify. Okay, so here's then what's going on. You might, for instance, have the state of the deck at the beginning of your time, where you know that the deck is in a particular configuration. So the probability of every other configuration is 0. Are you with me? This is the state of the deck. And now if I perform a particular shuffle, then it's going to move this, this state of the deck to some other state. Okay? So for instance, what this would do is if I do the top shuffle, let's see, top shuffle where you take a random card and put it on top, then what could result after one shuffle? So after one shuffle, tell me what possibilities occur. I guess if we're taking a middle card and putting it on top, I could get ABC, so that's one possibility with probability a third. I could get BAC, that's probability a third if I did that right. And I could get C, if I take the bottom card and put it on top, I could get CAB, is that right? And then everything else has probability 0. Okay? And what's just happened here in between is the shuffle. Are you with me? This is the top shuffle. It just basically took you from distribution to distribution. Are you with me? Okay, good. Let's practice. What happens after 2 shuffles? If I do another top shuffle, well, we will keep track of what's going on. This is after 2 shuffles. Then, let's see. This is a little more complicated. I guess what could happen is this probability then splits out over 3 options. This probability, 1/3 here, I guess A could go back on top, B could stay on top, C could go on top. So it would take you to CBA. That would be a new thing. And so what you see here is that all the masses here are going to move around. So if I think of this as lumps that are redistributing themselves, then help me out. I'll just see. So this one probably distributes itself out to 3 possibilities. This one, BAC, goes back to ABC. Let's see, what else could it go to? If I'm doing, take a middle card and put it on top. It could stay put, correct? And then it could go to CAB, CA, right? Okay. And then there's one more possibility. Just for fun, let's see. What could CAB go to? I guess it could go to ACB, correct? So that's a new possibility. And then it could go to what? Say again? BCA. Oh, that's a new possibility too. Correct? And then it could stay put, correct? Good. And so what you see is when you redistribute this stuff, there's 2/9 of the time it goes here, 2/9 of the time it goes here, 2/9 of the time it goes here, and now what happens to the other stuff? That's 1/9, I think. All the others are 1/9 possibilities. There's 1 out of 9 ways that could happen. Okay? All right, so after 2 shuffles, do you see that the distribution of what's known about the deck changes? In fact, it spreads out, doesn't it? Yes? Okay, so what do you expect to happen in the long run? They even out. That's what you expect, right? And that's what it would mean to be no knowledge of the deck. Wouldn't you agree that to be well mixed actually means every configuration is equally likely? Okay? That's what we mean by a random deck. Are you with me? And what I want to know then is, what is the distance of a given configuration from a random deck? Like here's a configuration, 2 nights, 1 night, 2 nights, 1 night, 2 nights, 1 night. And I want to know, I want you to tell me a way of talking about the distance between this configuration, this knowledge of the deck, and this state of the deck. So take a moment, discuss with your neighbor how you might talk about a distance from a random deck. Okay. Okay. I'd love to hear some of your suggestions. And there are lots of suggestions you could make. Yes?
For example, maybe standard deviation is a way to measure the distance from a random deck.
What do you mean, standard deviation?
Like, take all these probabilities. You already know that the mean is what is the probability you would get if things were even.
Okay. Oh, I see. So in other words, you're going to look at the pairwise differences here, and maybe square them and take the square root. Sum them, take the square root. Okay, that's one possibility. Are there other possibilities? Yes.
Take the average.
Take the average. Okay, that's interesting. Now, if you take the average of this, you get 1/6. And if you take the average of this, you'll also get 1/6. Because, so you could do that, although it probably wouldn't tell you as much as you'd want it to tell you, but that's a good thing to think about. Yes?
Take the average of division differences.
Take the average of differences. Okay, good. So instead of what you were suggesting, which is take the difference, square it, and sum, take the square root, you're saying just take the differences. And then do what? Average. Now, if you average those, you'll get 0. Because some will be positive and some will be negative.
Absolute value.
Absolute value. Interesting. Absolute value. Okay, good. So that would probably give you some measure then of how far apart they are. Any other possibilities? Suggestions? Yes.
Just find which one's the farthest one, and then that's like how far you are.
Oh, okay, good. That's another measure. You might just take the one that's farthest separated. Yes? Okay, so would you agree, in fact, there's lots of different measures here we could choose. Yes? And in fact, this is, mathematicians make choices often, and they make choices for particular reasons. So this involves a metric on probability distributions. And you have all named various metrics. I'll tell you the one that we'll use. There are lots of them, as I mentioned. So here's one choice. It's something called total variation distance. So this is the total variation distance. It's a very simple measure. It's basically take the sum of the absolute value of, if you don't mind, I'll call this P and Q. And a permutation, a configuration is going to be called pi. That's the tradition in math. So I take P of pi minus Q of pi, an absolute value, add up all the possible permutations, sum them, and add them. And instead of averaging them, which is what you suggested, I am just going to sum them. And if you sum them, what you realize is this metric lives between 0 and 2. Because the worst that can happen is that P has all its measures supported on some things, and Q has all its measures supported somewhere else, and this difference adds up to 1. This difference adds up to 1. They add up to 2. Okay? So it's traditional then to take this sum, because you want the number between 1 and 0 and 1, to divide by 2. Okay? This notion of distance between P and Q has some gambling interpretations. Okay? It's something like the amount you can make on a betting $1 if against an opponent, if you know the distribution is P, but your opponent believes the distribution is Q, it's basically the amount that you could make on a bet. Okay? The expected amount. Okay, good. So we need a notion of distance. That's the notion of distance we're going to choose for reasons that are convenient, which I haven't described. But it turns out the mathematical analysis is a lot simpler when you use total variation distance than it is for using, for instance, square deviation. Okay, so now I'm going to just tell you a very cool way of thinking about one particular shuffle, the top shuffle. Okay? This is actually a really deep idea. I didn't hear about this until I was in graduate school, but it's really just a very cool idea. So it's called the method of coupling. So whenever you have two random processes, if you want to understand one process and you understand the other, then what you do is you try to link the processes in such a way that an observer who only saw one process would think it's just evolving the way it normally does, and an observer who only sees the other process thinks it's just evolving the way it normally does. But behind the curtain, the two processes, you link them in a certain way. Okay? And what this amounts to is constructing what's called a joint distribution between these two processes. You may not have covered that in this class yet, but that's okay. Let me now tell you how this goes. This is really very, very cool. Here, I'll just draw a picture. This is easier. Okay, so here's what we're going to do. I'm going to imagine two decks. And in one deck, it's just going to be, so here's my deck. And now here's a random deck. Okay, let's just remind ourselves what I mean by random deck. Random means every configuration is equally likely here, okay? My deck is the one that I have, the knowledge that I know about it, my state of the deck, okay? So at the beginning of time, my deck is determined. That is probability 1 for one configuration and 0 for everything else. Are you with me? Okay. And random deck starts out random with 6 and 6 and 6 and 6, right? Okay. All right. So here's what we're going to do. So my deck is going to do a top shuffle, which basically means I'm going to take a card at random, let's say the 5 of hearts, and move it to the top. It just picks a random card. Okay. Moves it to the top. All right. Now, the random deck is going to be linked to this deck in a certain way. Here's what I'm going to do. Okay, who wants to be my friend today? Tell me your name. Jihan. Okay, so Jihan's going to be my friend. Jihan, her deck is random. It's already mixed. She has no knowledge of the deck. Are you with me? My deck, it started off, I know what it's doing. Okay. But now we're going to link Jihan's deck and my deck together. So what's going to happen is whenever I pick a card and move it to the top, Jihan is going to look not at the position, but look at the card. So she's going to search for 5 of hearts. If my card is 5 of hearts, she's going to search for 5 of hearts wherever it appears in her deck and move it to the top. Are you with me? Okay, so what's happened here is now, after this first move, would you agree our top cards are the same, correct? And if you just looked at my deck, it's evolving as usual. Random goes to top. If you just look at her deck, it's evolving as usual. Random card goes to the top. You don't know how she chose the card that she chose, but from your perspective, it looked random. It looked like just the top shuffle, correct? But they're linked. Okay, so what can happen next? Well, the next thing might be 7 of spades. I pick 7 of spades and I move it to the top. She picks 7 of spades and moves it to the top. Now, how many cards are the same? 2. The next thing that might happen is I pick 5 of hearts again and move it to the top. She picks 5 of hearts and moves it to the top. Now, how many cards are the same? Only 2 still, okay? What happened is that's because we happen to choose the same card, right, as before. But now, would you agree that the first time every card gets chosen from my deck, our decks must be the same, right? Because as soon as every card, a certain card gets touched, that many cards at the top are going to be the same, correct? And after all 52 cards get touched by me, that's when our decks look exactly the same, yes? My deck is random at that point because her deck is random. Are you with me? So I've just coupled the process. This is deeper than it appears. You're going to be like, yeah, that makes sense. And you're going to go home and say, no, it didn't make sense. I have to think about this. I mean, this is deeper than it sounds, okay? So what's happened is we've coupled the processes so that from her perspective, random just evolved. Random stays random. Random, state of the deck. But then my deck has suddenly gone from now knowing where it is to completely random as long as every card gets picked. And how long does it take for every card gets picked? First time every card is touched, the decks are together. This is related to a classical problem called the coupon collecting problem. And the expected number of steps until you touch every card, until you collect every coupon. You might learn about this in this class, I don't know. This is known to be n log n steps. Okay, so for 52 cards, this is log, natural log, that's 200. I think 52 log 52 is about 200. Okay, so it basically takes about 200 moves, top shuffles, to mix this deck. Yes?
Okay, so at the beginning you knew the order of her deck and Jihan didn't, and next time you shuffle it, you don't know what card you're putting on top, but Jihan knows what card she's putting on top. So how is hers random at the end because she knows what card she
Yeah. Well, if you just look at her distribution, the probability of me picking 5 of hearts is 1 out of 52. Probability of me picking 7 of spades is 1 out of 52. So if she couples her deck to my deck, and it already started with equal likelihood, it's going to evolve. It's just going to look like a top shuffle, right? The chance of any particular card getting picked and putting on top is 1 over 52. So it looks the same. Yeah, something deep going on. Yes?
Do I only need to touch 51 cards?
Yeah. Yes,
the
that's
last
correct.
one's
Yes,
on
that's correct. Yeah. Touch every time. Yeah, you only need to touch 51. That's correct. Okay, good. So this is one way to analyze a particular shuffle. Like we know now this is actually basically about 200 for 52 cards. All right. Let's talk about the GSR shuffle. So this is the one that we really want to understand because it's the way most people shuffle. It is there's multiple ways of understanding this shuffle. And the fact that there's multiple ways actually means there's something deep going on. Okay? So the usual way to understand it is you cut the deck binomially. So what does that mean? It doesn't necessarily mean half and half, but it means it's quite likely to be close in size. And what that means is flip 52 coins, count the number of heads, and then cut at that number of heads in the deck. Okay, so if you see 24 coins, you cut 24 and 28. You with me? So there's a probability going on right here. And then what you do is there's more probability going on. Once you cut the deck, you drop from one side or the other proportional to the number of cards on that side. Okay, so if I see 3 cards here and 4 cards here, the next card comes from this pile with probably 4 sevens. Are you with me? Okay. So that's the usual shuffle. It's the way you think about shuffling. It makes sense. And actually, people have modeled how people shuffle, and it's a pretty good model. All right. The second way is interesting. It says cut binomially, but then of all the possible ways you could interleave, some of them could be quite lopsided, choose them uniformly across all of them. That is the same probability. Turns out that gives exactly the same probability distribution of permutations as the first. Here's another one. Take all possible ways to cut the deck and all possible ways to interleave and pick among them uniformly. That turns out, surprisingly, to be the same. Here's another one. This is called the inverse shuffle. You take a deck of cards like this, and and you assign a number, coin flip, heads or tails for every card. H, T, H, H, T, 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 H, H, etc. And then all the cards marked H you pull out one side, all the cards marked T you pull out the other, and then you put one on top. So this is the opposite of the shuffle. It's you pull them apart and stack, yes? That's an inverse description of this shuffle. That's another way to think about this shuffle. Last one, I like this, it's really beautiful. Here's one. Take the unit interval, 0 to 1, and put 52 random points down on this interval, picked uniformly. Okay, 52 points down. And so what does that look like? That looks like this. So, you know, there might be some clumping here and there, yes? So here's some points. Here, those are 7 points, yes? And now, stretch them, multiply by 2. Yes? And now cut exactly at 0, 1, and then move this deck, this side over here, and that produces an interleaving of the deck. Put them together. Okay? That is very geometric description. Turns out to be equivalent to card shuffling as well. If you want, I mean, this might be very easy to model continuously. Okay, these are all equivalent ways of understanding the shuffle, and they're beautiful, and they turn out to be quite useful. Here's another way to think about the shuffle that's also helpful in understanding them. So here, instead of cutting into 2 packets, cut into A packets, and then interleave. Okay, so cut, put them together, okay? It turns out that, so what we're talking about, the regular shuffle is a 2 shuffle. But it turns out that a 2 shuffle followed by a 2 shuffle is actually a 4 shuffle. And a 3 shuffle followed by a 2 shuffle is actually a 6 shuffle. Okay, so these are, you can convince yourself very easily if you just think about the geometric version, right? Multiply by 3, multiply by 6, cut and interleave. Each of these descriptions will help you see that these are actually the same. Instead of cutting binomially, you cut multinomially. Okay, so that's another ingredient of this proof. So I'm just sketching to you now some ingredients. So here's another ingredient of the proof. It's kind of nifty. It turns out, if you think about what's going on with a regular riffle shuffle, that after one shuffle, there's still some structure. Okay? So what's the structure? Well, if it's an 8-card deck, maybe, let's say, it gets cut into green half and a yellow half, and then they get interleaved in some way, yes? Would you agree that after one shuffle, the set of things you can see isn't everything? In particular, the only things you'll be able to see after one shuffle are things that have what are called 2 rising sequences. That is, if I go through the deck in order, 1, 2, 3, 4, 5, 6, 7, 8, I actually have to pass through the deck twice to see all the cards in order. Are you with me? And a riffle shuffle always produces something with at most 2 such sequences. They're called rising sequences. Okay? So for instance, this creature could not be the result of one shuffle. Why? How many passes does it take to go through the deck to see all of them in order? Ace, 2, 3, whoop, 4, 5, whoop, 6, whoop, 7, 8. I don't know what that noise was, but those are the dividers between the shuffles, yes? The rising sequences. Okay, so you can't get this after one shuffle. You can get this. What happens after the next shuffle? Well, after the next shuffle, this might get cut in some way. We don't know exactly how. But do you see that when you do that interleaving, each of those rising sequences got split in half, and so you might have up to 4 rising sequences. Are you with me? You might have fewer if some of those things didn't actually overlap, right? Like if this 4 had appeared after this 3, you might have fewer. But you can't have more than 4 after 2 shuffles. Are you with me? Okay, so this is an important point with rising sequences. How many rising sequences then do these creatures have? How many here? 1, because you can go through in order. You don't have to go around. How many here? Ace, 2, 3, 4, 5, 6, 7, 8. Yeah, 3. 3 passes through the deck to get them all in order. Yes? How many does this one have? Looks like 5. You can verify. How many does this one have? 8. Why 8?
Reverse order.
It's reverse order. Ace, 2, 3, 4. You have to keep going to get them all in order. Yes? Okay. So, by now we already see that the riffle shuffle what do we already see? Let's see. After 2 shuffles, you have at most 4 rising sequences. Yes? After 3, at most what? 8, because they each get split maybe. At most 4, you have what? After 5, how many?
32.
And so, is it possible then to take a 52 card deck and reverse it after 5 shuffles? No. Already we see 5 shuffles are not enough to mix a deck of 52 cards. Are you with me? Because not only is not every configuration equally likely, you can't even get the reverse deck after 5 shuffles, yes? So it's a little surprising that it only takes a few more shuffles to mix the deck. So here's another ingredient in the proof. If you have a ordered deck and you put in dividers where the cuts are going to go for an A shuffle, then these dividers help determine what this configuration looks like. Okay? And if you put in more dividers and you want a certain number of rising sequences, then you can put them anywhere, because only some of these are going to determine the order that they go in. And so if you want to count the number of the probability of getting a particular permutation, it turns out it only depends on the number of rising sequences in the deck and the type of shuffle. So this is an N, so it's it looks like this: N plus A, choose R, choose N, over 2 to the A, where A is the number of shuffles, N is the size of the deck, and R is number of rising sequences. This is using what's a standard combinatorics argument known as stars and bars, if you've heard of that. If you haven't, don't worry about it. But the point is, you can actually easily figure out the probability of any configuration. It only depends on the number of rising sequences in it. So if you do a little bit of analysis, what you end up finding is, in fact, the total variation distance from a random deck looks something like this. It's quite surprising, actually. So this is N, this is the number of shuffles. And here is the total variation distance from 0 to 1. And it turns out then that the total variation distance stays very close to 1, and then it steeply drops off, doubly exponentially towards 0. And where it happens actually happens near 7. 5 shuffles, it's very close to 1 still. In fact, you can't reach every configuration. At 7, it drops off steeply. And so this is where you get this result. So this is actually a famous result now of Bayer and Diaconis. Diaconis was my PhD advisor. And this is proved in 1992 that basically 7 shuffles makes a deck. Now, it doesn't mean that more shuffles still makes the deck further, but the idea is that there's a cutoff. And if you want to know the general cutoff for N cards, it turns out to be approximately 3/2 log base 2 of N, which is also a surprise. There's the paper, Trailing the Dovetail Shuffle to its Lair. It's actually quite readable for a paper, and also of applied probability. You could look it up, probably find it pretty easily. And it's, I think a beautiful description of a combination of modeling, some beautiful math, and some, it sort of confirms the intuition. Like, if you think about this a little bit, Why is it that after 5 shuffles, you can't even reverse a deck, but after 7, it's pretty close to well mixed? Here's one way to think about it. If you imagine a 7 shuffle as a 7 shuffles, 7 2 shuffles as a 2 to the 7 shuffle, that's a deck where you break it into 128 pieces, yes? And when you break a deck into 128 pieces, most of those pieces are size 0 or 1. And so then if you interleave them in some random way, that's basically like 52 cards to them. Okay? So that's another way to think about why that happens. If you'd like to see how I prove, oh yeah, if you want to see this card trick, I'll just finish with the conclusion of this card trick. Or I could just let you all go home. You want to know how to do this?
Yeah.
This is great. This is such a great trick.
Don't tell anybody the secret.
Okay.
I'm going to have a recording off.
Yeah, that's right. They're not going to like you for that. Doesn't matter. This is a cool trick. Okay. So what actually happened with your deck? What happened is the following. So before the class started, I actually ordered the deck. Surprise, surprise. In a particular way, such that when I display them to you, it doesn't look that unusual, unless you stare closely. And then you realize, if you stare closely, that it is, they're all perfectly alternating, yes? Red, black, red, black, red, black. But when you display it, no one's going to tell, yes? Then you give it to a volunteer, and the only thing you have to remember about this trick is that you have to cut the deck. Okay, so I handed the deck to him, okay? And the way I cut it is I have to cut it so that the bottom cards are different colors. Are you with me? Okay, so then I hand it to you and I say, please interleave them, yes? If you forget this piece, it's only half the time it's going to work. Okay, now what's going to happen when Chan takes the deck? Well, let's see. So can I predict which card's going to fall first when he does the riffle shuffle? No. But suppose it's the red one. If it's the red one, what's the next card have to be? Black. No matter which side it comes from, yes?
Oh
my gosh. Whoa. Even if it comes from the same side, like even if he clumped, because then we're back to what situation? Red, black. Which side's going to fall? Say, I don't know.
I don't know.
Okay, this time maybe, suppose it's black, then what's the next card have to be? No matter what. It's red, yes? And so no matter what happens, even if they start all coming from the same side, they're going to come off in red, black, or black, red pairs. Are you with me? And so what will happen is, by the time you look at it, it's not going to be perfectly ordered red, black alternating anymore. Do you see? No longer is it going to do that, yes? But they will be in red, black, or black, red pairs. Yeah? And so the only thing you have to do it for the benefit of the audience, the only thing you have to do now is to make it look difficult. So you're like, oh, I have this amazing ability, and you're like fishing around. It sounds like you're fishing around in the deck somewhere, but you're just picking them off the top. 2 by 2 by 2, all the way to the bottom of the deck. Anyways, thank you for having me today.